Hi. Today I wanted to show you how to draw bending moment diagram, how to draw shear force diagram. And let's start with a simple example. But in this example, I consider the all types of loading, like point load, uniform distributed loading, and point moment that apply to a simply supported beam. Okay, let's start that. This is simply supported beam with hinge at A and roller at B, and one load is applied here at zero point 0.5 meter, 10 kilonewton. The uniform distributed load applied here from 1 meter to 2 meter. Density or intensity is equal to omega is 5 kilonewton per meter. And a point moment or concentrated moment M is 10 kilonewton applied here. And we wanted to draw it's actually, uh, yeah, shear force diagram first. Before do anything, you must draw the free body diagram. Free body diagram means separate all surroundings and supports from the beam and put the effect of them on the beam. Okay, let's draw the beam again. For hinge support, we have two reactions because the hinge actually doesn't allow the beam go back and forth or up and down. Then two forces in x and y direction. You must substitute for any pin joint or pin supports in beam. For the roller support, it just doesn't allow it go up and down. The beam is free to move or for expand, for example, here. Then the only effect of this roller is a force upward. Then here, other loading conditions, I show them again. This is 10. This is the distributed load, 5 kilonewton per meter. And this is the concentrated load moment, 10 kilonewton per meter. Let's correct this one as well. Then, after that, when you draw free body diagram, then you can start to calculate the external reactions or support, actually, reactions here. The first equations that you can write is summation of forces in x direction, horizontal forces. We don't have horizontal force here. If we had here, then this AX must actually be in balance with them. But the only force that we have is AX, and it is equal to 0. Then we cancel this force out. We do not need this anymore. The second is not summation of forces in y direction. Summation of forces in y direction actually, because we have here Ay and By, two unknowns, this equation doesn't help at the moment. We don't waste our time because if we solve summation of forces in y direction equal to 0, we reach to an equations that has two unknown, and we cannot solve that. We have to keep it actually in place until we can find one of the unknowns, Ay or By. But the second is better always write summation of moments in A or B must be 0. One of the support. Why A or B? Because I wanted to cancel out one of the reactions, one of the unknowns. This is why I take moment at A or B. That's the simplest way. Shortest, fastest, and simplest way. Okay. Let's talk about summation of forces of moments in B at B equal to 0. Then the only thing that you must do in here, any uniform or non-uniform distributed load must convert it to a concentric or point load before solving reactions at the support. Then this load here is 5 start from 1 to 2 meters. 1 meter length times 5 Newton per meter, kilonewton per meter is equal to 5. I show its equivalent 1, 5 kilonewton. And then I don't want this uniform distributed load at the moment. Just you have to get rid of that for calculating the reactions at the support. Then let's start to take the moment at B. Pi times the length, which is here 3 meter distance. This is 0.5, this is 1 meter, this is 2 meter, this is 2.5 location of them. Then Fy times 3. It produces a moment in clockwise. Textbook actually consider clockwise, most of the textbook negative, and counterclockwise rotation for moment positive. Then Fy is clockwise. I put it negative sign here. 10 times this distance, which is 2.5 meter, and produces counterclockwise, then positive, 10 to 0.5 meter. And here the equivalent of the uniform distributed load will act at this point exactly in the middle of the beam and is 5 times 1.5 meter from here and produces clockwise as well. And the moment here, the concentrated moment or point moment here, we just add it because it is clockwise is positive and is equal to 10 and then nothing, 0. By solving these equations, you reach to 25 plus 1035 plus 7.5, 44, 2.5 divided by 3. Y is equal to 14.167 kilonewton. Okay, that's the result. We wanted By. If you want Dy, you can take moment about Ay, one method. Another method is use here. Summation of forces in y direction is 0. That's better and faster. Then, if I write, let's move this one. If I write, I can write here, summation of forces in y direction is 0. Then, Fy minus 10, minus 5, and the only thing that we have plus By equal to 0. What is Fy? 14.167 minus 15 plus By equal to 0. By is equal to difference between these two, which is 0.833 kilonewton. Then, that's the first step. That's the static part of the problem. Solve the beam, find the external reactions with different types of loading. Then we don't need these calculations anymore. I need more space. I have to erase them. Okay? Remember, just two numbers. 14.167 and 0.833 kilonewton. Then we return back. I delete this equivalent and I return back to my uniform distributed load again. That was only for finding the external reactions at the support. Okay, let's start. Go step by step. Loading conditions to draw bending moment diagram or shear force diagram is very important because you have to cut the beam. And the number of cut depends on the loading conditions. If the loading conditions from the first to the end doesn't change, one cut is enough. But if step by step you see that the loading condition like this beam changes, from here to here no change, we say, okay, we need one cut. But here we have a before and after 10 kilonewton. Make it clear. We have a before and after 10 kilonewton. Then it means that the loading conditions is changing. Then we need a cut here as well. From 0.5 to 1, nothing changes. This one cut is enough. But when we enter the uniform distributed load, we will see it is continue. Nothing is changing till 2 meters. Then only for this one cut also is enough. After we pass 2 meters, we see that the condition changes. No uniform loading. Then we need one cut till we reach 2.5. Okay? And when we reach to here, okay, loading condition changes because of 2.5 kilonewton meter to, 10 kilonewton meter at 2.5 meter. Then after that, nothing happened till the support B. Then we need one cut here. How many cuts we have here? 1, 2, 3, 4, 5 cuts to draw the shear force or bending moment diagram. Then let's start with the first. I cut it here. This is the force 14.167. The length that I cut from the origin A till the cut section C is called X. Always from the origin to where you cut you give an imaginary cut to the beam is called X, because we take the origin at the left side and x-axis will be here. Okay? Then, according to the convention of static books, we have to put the shear force downward for the left side portion and counterclockwise M for the right side. If you wanted to consider the left side, when you give a cut to a beam, you have two pieces, left side piece, right side piece, left side portion, left side, right side portion. And for the right side, if you wanted to consider the rest of the beam, maybe you think it is easier, you do it. V is the upward and M is clockwise. That's a convention of most of the text. Okay? Then we started from the left side. We do not need to consider the right side. And then our job is to calculate amount of V and amount of M at the C cut at the point C. Okay, the first thing that you write, summation of forces in Y direction. Because V is in the Y direction, and we need just summation of force. What we have? And here 14.167, here minus V, which is downward negative, then V is equal to 14.167 kilonewton. And then for the M, summation of moment at C equal to 0, then 14.167 times X is clockwise, negative sign, plus M equals 0. You get M is equal to 14.167 X. That's it. I write this answer here because I don't need these calculations anymore. At we say at x is between, sorry, the range. X is between 0.5 and 0. We got this one. V is equal to 14.167 kilonewton, and M is equal to 14.167 x. Is a linear equation, first degree. Let's go for the other part. Do this cut, 14.167. We cut from here. This is again x. We have a force here at 0.5, 10. We got ay 14.167. We have nothing else. Just put V and M and calculate it. Again, summation of forces in y direction 0, 14.167 minus 10 minus V equals 0. Then the difference is 4.167 minus V. V is equal to 4.167 kilonewtons. What about M? Take moment at C equal to 0. You got here 14.167 dot x times distance x plus 10 times this distance. This distance, because we know the whole distance is x, this distance is half meter less. Then it is 10 because it produces, this produces clockwise negative sign, this produces counterclockwise positive sign. 10 times the whole length x minus 0.5. The whole length x minus 0.5, which is this one. We can write it x minus 0.5. That's the distance. Plus what? Plus m. Equals 0. Calculate m. This is 10x plus minus 14x is 4.167x. And what else? 10 times 5 plus 5 plus m equals 0. M is equal to 4.167 minus 5. 4.167 minus 5. Minus or plus is minus. 10 times this is minus. No, minus. And then it became plus. Okay. Then we just need to write the result here. X is between 1.5. V is equal to 4.167 and M is equal to, don't forget it's here, 4.167x plus 5. Okay, I do not need this derivation anymore. And this part also. Let's go for the third cup. Okay, this is the important one. Why? We have here 14.167. At 0.5, we have a 10 kilonewton. At here, 1 meter, it starts a uniform distributed load, a function of that, till the cut section. We have here C, V downward, M counterclockwise. Then let's write again sigma Fy equal to 0. It means that 14.167 positive minus 10 negative minus, this is 5 kilonewton per meter, times the length you must substitute with a here equivalent resultant of this uniform distributed load. How much is it? It's 5 times the length. How much is this length? The length is this amount. The length is this amount equals to the total length x minus 1. Total x is x minus 1. Then 5 times x minus 1 is the force. Okay, write it here. Minus 5 x minus 1 equals 0. Well, when we split, then minus v equal to 0. Then simplify that. 14.1 minus 10 is 4.17 plus 5 is 9.167, and then minus 5x, yeah, minus v equals 0. V is equal to 9.167 minus 5x. Okay, that's the resultant for V. At x is between 2 and 1, between 1 and 2, V is equal to minus 5x plus 9.167, and M, let's calculate it. Summation of moment about C is equal to 0 again. 14.167 times x negative clockwise plus 10 times, what's the distance? Here to here. This is x minus 0.5. That's the distance. This is 0.5. The whole length is x minus 0.5. Then this is equivalent. Amount both produces counterclockwise plus 5 times x minus 1 is the load. That's the load applied here. What is this distance? Times this distance. The whole length is x minus 1. This is the middle of the x minus 1. Then is x minus 1 divided by 2. Then this distance is equal to this distance, which is x minus 1, divided by 2. Okay? Plus m equals 0. If you simplify that, then you have a 4 minus 14x plus 10x plus 5x. This is, I made this simple. This is minus 4.167x here, plus minus 5. Here is plus 5 over 2 is 2.5 times x2 minus 2x plus 1 plus m equal to 0. Then, again, here I have 2.5 times minus 2x is 5 minus 5x plus this is minus 9.167x. Okay, I cancel out this 2. I have 2.5x2, and I have minus 5 here. Plus minus 5 plus 2.5 here is minus 2.5 plus m equals 0. Then m is equal minus 2.5, m is equal minus 2.5 x2 minus plus 9.167x plus 2.5. That's x is between 1 and 2. Then, if we move a little, we reach to the fourth cut. We do not need these calculations. We put the result over there, and I can move a little camera that you can see the whole equations. Okay, yeah, let's cut from here. Some students, when reach to here, they see that the right side portion is smaller and is simpler than the left side. But I follow this one because let's stick to the left side portion of the. Then, when you pass through the uniform loading conditions, then it converts to its equivalent, the concentrated load. If you are inside, this is distributed. When you pass it, it is just a uniform, is a concentrated load, which is 5 times 1 is 5 kilo Newton. We get rid of that anyway. Okay. Then this is 10. This is 14.167 and nothing else. You have a V here, an M, and X is between 2.5 and 2 in this portion. Okay, let's write the, everything is here similar. Summation of Fy equal to 0, 14.167 minus 10 minus 5 plus minus V equals 0. V is equal to minus 15 plus 14.3 is minus, yes, minus 0.833 kilonewton. Then I write it here. X is between 2.5 and 2. V is equal to minus 0.833 kilonewton. We do not need these calculations anymore. Let's go for moment. Summation of M with at C equal to 0. Then we have 14.167 clockwise x. Don't forget this distance to C is x. And minus this, plus 10 times this distance. Let's write the distances. This one, this is x at x is equal to 1.5 meter. This is x minus 1.5. And this one is x minus 0.5. Okay, 10 plus 10 times x minus 0.5 plus 5 times x minus 1.5 plus m equals 0. M is equal to minus 14 plus 10x plus 5x is 15, is actually plus and minus 0.833x. 10 times minus 0.5 is 5, minus 5, minus 7.5, minus 12.5. Go other side, plus 12.5. That's M. That is x is between 2 and 2.5. M is equal to minus 0.833x plus 12.5. Yeah, we do not need this anymore. we reach to the end. It is clear from the end, if you give a cut here, V is equal to 0.833. But because you consider the other side, the V will be upward. V plus this equal to 0, V is equal to minus 833, and the moment also is very easy. Just you have this value 0.833 times 3 minus x. But I consider the left side because I just stick to that. And here, that's a beam. That's the length of it x. And then distributed in the middle of the beam is just 5 kilonewton at 1.5. This is 10 at 0.5. And this is 14.167 at A. And this is M 10 kilonewton meter. And here we have a V at C, and here we have a M. How much is V? Summation of forces in Y again 0, 14.167 minus 10, minus 5, nothing here, this is concentric moment, not force, minus V equal to 0. You will find out minus 15 plus 14 is minus 0.833, and goes to the other side and becomes again negative. The same as here, because the moment doesn't change anything here. Where x is between 3 and 2.5. What about m? Summation of m at c equal to 0, 14.167 at x, minus plus 10 at x minus 0.5, this distance, plus 5 at x minus 1.5, plus 10, because it is counterclockwise, plus m equals 0. Then this is minus 14.167. This is 10x, this is minus 15. Then we have a 0.833 here as well, x positive. Here is 5. Here is minus 5, minus 7.5, minus 12.5, plus 10 is minus 2.5. Then m is equal to, this becomes negative 0.833x. We get rid of the x. Then we have here 5 plus 7 minus 5 minus 7 12, minus 12 plus 10 is plus 2.5 minus, actually this is minus 5, this is minus 7.5 minus 12.5 plus 10 minus 2.5, and then we have to, yes, the direction will be changed because I bring them the other side. This is m, actually, that is m equal to minus 0.833x plus 2.5. If you want to check that you didn't mistake during calculations or not, you can check them at the border. For example, at 0.5, we must get the same value for V and M in both. If it is 0.5 here, it doesn't matter, V is constant here. And here, V also at 0.5, if you put V there, is 4.6, 1.6, because we have a 10 kilonewton force that there is an abrupt change due to 10 kilonewton. But this is not x. We must change the equation in terms of x. Here, if you put half a meter here, you get to reach to 7.08. And if you put half a meter here, you just get 7, half of the 4.167 divided by plus 5 is 7, the same as here. You will see you didn't make the mistake here because you check them at the common points. For example, between these two, if you put here 2 here, it is 2 times this is something like 8 plus 5. And if you, for V is here, oh, here is M at 2, and M at 2 here is this one. Then this multiplied by 2 plus, which is negative, plus 12.5, which reach again to that value again. Okay, then everything is ready to draw the bending moment and shear force diagram. I get rid of this and I go. I do not need these beams anymore. Just I keep the original figure of the beam and draw step by step according to the equations. First, V diagram, 0.5, 0.1, 0.2, 1.5, 3 meter. Okay. Equations is 14.167. 2, 4, 6, 7. It goes very high. Let's go 4, 8, 12, 14, better, or 16. This is the origin. 14 here, 14.167, close to here, till 1, off. And then for x between 1 and half and 1, we have 4.167. It means 10 abrupt change here, till here, between half and 1. And between 1 and 2 is an equations with negative slope, minus 5x, we got this point. For the straight line, slope straight line, you need 2 points. We got 1 point here, 1. And the other point is 2. If you put 2 here, is minus 5 times 2 is minus 10 plus 9.167 is minus 0.88. You got it here. And then connect them together. Here you got minus 0.833. After that, V is constant, 0.833 between 2 and 2.5. And again, is constant, minus constant, 0.833 at here. That's the shear force diagram of the beam. That's I show you. Let's go for drawing bending moment diagram. Bending moment diagram, just use the equations. First, M is 14.167 between 0 here and half. If you put it, it is 14 at half is 14.167 times a half is 708, something like that. It is, if you average 7.08, you reach to this point. Straight sloped line. And then M is 4.167 x plus 5. We have 1 point. We must find another point here at 0.5, 0.1, find that over, is 9.167. Here you got this curve, 9.167. This is 7.08 kilonewton meter. This is M. Don't forget unit, kilonewton meter. Then draw it between 1 and 2. Between 1 and 2, M is a parabolic. Is a parabola equations with the second degree. 2.5 minus 2.5 x2 plus 9.167. For this one, you need 3 points. 1 point is here. 1 point, for example, you can find it here that passes through, so this is the maximum point of the bending moment. You can find the coordinate of this, or you can put 1.5 here in the middle at this equation. Then x is equal to 1.5 and x is equal to what? X is equal to 2. You got 3 points for that. For example, here, and 2. At 2 is equal to minus 5 plus 18 is plus 13 plus 2 and 5 is 15, something like that. 2.5, 2, okay. 2 must be, 2 power 2 is 4 minus 10 here, minus 10 here, plus 18, something like 8, plus 2.5, 10 point something here. But in the 1.5 is larger, it is similar to this. You want to exact, that's the shape of the bending moment of this one. If you want to exact, find this exact actual value. Then at between 2 and 2.5, it is 0.833 x plus 12.5. If I multiply 2, by x plus 12.5, I reach this one. 12.5, I wanted the value of this, 12.5 times 2 minus 2 times 0.833 plus 12.5 is 10.831. That's valid. If you wanted to find out another point, you just put on the between 1 and 2, 1.5 to power 2 times 2.5 is negative plus at 9.167 times 2 plus 2.5. Yeah. 5, 2 times 2.5 minus 9.167 times 1.5 minus 8 minus 2.5 is 10.62 is here. You will see 10.8 here. It must go over a little different. You want to draw exact shape. The maximum should be here, because V is 0. Then we have this point at 2 and 2.5. If you draw it, minus 833 plus 12.4 at here, there is also a straight negative slope line, which we wanted to find it at 2.5 0.833 times 2.5 minus 12.5 is 10.41. It's less than that. Something like that. 10.4175 kilonewtons. And then between 2.5 is a straight line because the function is a right, first line is x. Like y is equal to x plus b, ax plus b. Then the last one, minus 0.833 x plus 2.5. Okay, at what? At 3. At 3, at 2.5, we have a value here. Why? If I go to draw between 2.5, if I give 2.5 to this, see what we have. 0.833 times 2.5 minus 2.5 is 0.4175. It's not the same. You see, we have a 10 kilonewton abrupt change downward because of this moment, point moment that applied here. And then at the end, I know that this is a simply supported beam is 0. Okay? Then, and at 2.5, it is equal to this one. Then I attach these two by a straight line. This is the bending moment diagram that we draw it. This is the bending moment diagram. And let's show you again the equations that you have, see all equations, and show the curve, bending moment curve, and shear force curve as well. That's how to draw shear force and bending moment diagram. The only thing that I didn't consider here is a distributed loading which is variable, like triangular distributed loading or curved distributed loading. In this case, moment here for triangular, we have a second parabola in shear force diagram, and third, actually, degree of curve for the moment diagram. I leave it for another actually example, and let's leave it here. We finish that. Thanks for watching, and